You're listening to WonderLabs, filling your ear holes with nerdy goodness.
Hello and welcome to WonderLabs. I'm Ellie Mackay.
And I'm Chris Richardson.
In this episode, we speak with Joanna Huang. Joanna is a researcher in high-energy physics and splits her time between University College London and CERN in Geneva, which houses the largest particle collider on the planet, and is where she's involved with the ATLAS experiment.
We distill some fundamental concepts in particle physics and the work happening over at CERN, before diving into discussions on time travel, the origins of the universe, and one of the focuses of Joanna's research, dark matter. We also discuss the challenges of working in a field with less tangible benefits than many other fields of research.
The discovery of the Higgs boson is arguably one of the most important scientific discoveries of our lifetime, and it's great to have somebody close to that work on the show, and someone who is also a fantastic voice for women in physics.
Joanna really manages to distill some dense and difficult topics in an interesting and accessible way. We hope you enjoy this journey through time and space. Joanna.
Hello.
Particle physicist. I've been super excited about this conversation, as has Ellie.
You're one of the people that actually gets to say, I'm a particle physicist.
Yeah, it's pretty cool.
How cool is that?
Yeah.
So
is that just like a mic drop moment anytime anyone asks you what you do? It's just like 5 seconds of silence.
Get up from
afterwards.
the dinner table, leave the pub, that's fine.
I think that beats brain surgeon or rocket scientist.
Like, totally, yeah. I feel like, yeah, so it's just abstract, and it's one of the things that I don't think is very well understood, and which is why we're really looking forward to picking your brains.
We're gonna unpick it all.
So let's do it then.
Yeah.
So tell us a bit about your background and how you got into your current line of work and where you are at the moment.
All right. So it wasn't always physics. I feel like a lot of people that I meet in physics love it and loved it from the get-go. But I started my undergrad in biology, and then I switched to psychology, and then I wanted to be a psychiatrist, and then I was applying to medical school.
Wow.
And then 3 years into my undergrad, I didn't like that anymore, and then I swapped over to physics.
What made you swap to physics? That's quite a big leap.
Yeah, it is a big leap. Yeah, I've always liked physics, and I've always been very keen on the math, but it was too intimidating a subject, so I didn't think that I could ever, make it.
I want to pick up on that point that you've made, because I think it's really interesting. It's something that our listeners would really value, that idea that you went into a topic that you were interested in, the biology, the psychology, and then you changed to something else afterwards. And firstly, a lot of people don't know that they can do that, or
especially in the UK,
they're scared that they can do that, because we're told you're a scientist or you're an artist, and then you're forced into one specialism, and you have to choose at 17 what you're going to be. So it's quite reassuring, I think, firstly to hear from you that you did lots of other subjects and then found your way into physics, and secondly the point that you thought that physics was intimidating.
Absolutely.
You wouldn't be able to do
Yeah,
it.
very intimidating.
Why do you think that was?
First of all, my gender. The gender ratio in physics has always been horrible, and maybe 10% of us were girls, and one of my most stark memories was, so this was just a mandatory physics class that everybody in sciences had to take. We had to pick lab partners, and of course, the two girls in the room get left out, right?
Oh gosh.
Nobody wanted to work with the girls because they just have some sort of presumption in their brain, you know, conscious or subconscious,
That's all too familiar, I think, for a lot of young women and girls interested in science listening. That will be very familiar.
Yes.
But actually, I think as we move forward and we have people such as yourself moving into the realm of research and providing those strong, positive role models, and
so you are now such a fantastic ambassador for women in STEM. What sort of ratio is the gender now in your current lab?
In my current lab, less than 10% are female. Yeah, in my year, there are about 21 new students, 2 girls.
So do you feel sort of a sense of responsibility that you're carrying this kind of burden of you've got to represent your entire gender, even though you're only 10% of the lab? Or do you not see it at all? You don't worry about it?
No, I see it. You stick out like a sore thumb if you're a woman in physics. And then if you add like a racial background, ethnic background to it, you stick out even more.
Right.
But I feel that because of that, it just makes me want to prove a point, anybody who said there aren't many women in physics, like, you better be careful, it's a tough field, It's stuff that I've been told a lot by people who mean well, but then it's just kind of like, well, I'm gonna make
drives
it.
you and motivates you to
You
be
just
that role
watch.
model.
Brilliant.
And that's
so
what we need
good.
as well, I think.
Yeah. But I think it's really improving. Every single university nowadays has a women in physics program going on.
Yeah.
There's conferences for promoting women in physics, and all of the men in the department are really proactive about it. So I think this is a good time.
That's good to hear.
Oh, that's good to hear.
So then coming back to where you're at the moment then, particle physics, high energy physics, those two, are they synonymous? Are they the same thing? Could you maybe define for us what exactly is the domain of particle physics?
Yeah, particle physics and high energy physics are synonymous, and it just means physics conducted at a very, very high energy level, and you're studying something on the particle scale. And
Just to really break that down, what do you mean by particle?
by particle, I mean literally everything that you can see, touch, feel, hear.
Matter is made up of particles? Is that,
Yes.
Is that
yes.
too reductive of...
No, that is absolutely perfect. So everything, all matter is made up of subatomic, tiny, tiny little particles stacked together in some formation.
And what sort of scales are we talking about?
Okay. Maybe in one paper clip, right? Let's say that paper clip was made fully of one sort of atom. It was just iron in there.
Okay.
It would be 10 to the power of... God, a lot. 16. So one with almost 20 zeros behind it. Iron atoms making up that one small
That's like
little
a trillion,
paper
trillion,
So
trillion.
Gazillion, billion,
billion,
atoms.
manillion.
yeah.
So that's okay. We're talking really, really small.
So are
Yeah.
we're talking, because I know, so you have millimeter and you have micrometer and you have nanometer, but then you have picometer and femtometer.
Yeah, this
You're
goes
way beyond that,
and at
far
this
down the rabbit hole.
yeah, way far down, and it gets so small that we don't use the measurement for sizes anymore because you can't measure it very precisely. So instead, you use how much energy they have.
That brings us on to
Fantastic.
something actually then, and you're trying to measure that energy as part of your work with CERN. What does CERN stand for?
CERN stands for the Organisation Européenne pour Recherche Nucléaire. So it's a French abbreviation.
Such good pronunciation.
Right,
as
so it's
well.
the
European
European
Organization for Nuclear
Nuclear-
Research.
okay.
Yeah.
So
and
in
it's
English it would be European.
so,
CERN is better.
but it's a French. So and famously been in the media in recent years. You know, it's this huge collaborative effort with scientists from across Europe, and it's a centre that spans the border of Switzerland and France.
Yes, so it's on the Swiss-Franco border. It's very, very big. It's a gigantic particle collider, and by that I mean they take these tiny, tiny particles that I'm talking about, and they accelerate them around a ring. Right?
And this
So-
is the Large Hadron Collider that people may have heard about in the
yes,
news.
the LHC.
It's a circular ring, isn't it? A
Yeah.
tunnel,
It's
essentially, like a donut.
It's an underground
Underground.
tunnel, and the circumference of it is 27 kilometers.
Uh-huh.
So it's very, very big.
And we're accelerating these tiny particles so that they have a high energy.
Yes,
And-
so that they go close to the speed of light.
Okay.
Which
So-
is how fast, roughly?
Speed of light is 3 times 10 to the 8, so 3 with 8 zeros behind
Yeah.
it, meters per second. So if you think
Gosh.
about it, the distance from Earth to Sun takes like 7 seconds to travel.
Yeah.
7 seconds!
Wow.
So when you're looking at the sun in the sky, it's actually moved from its position.
Yeah. Well, also that's true with stars. That when you're
Yes.
looking at stars, a lot of them don't exist anymore
Yes.
because it's so far away
Yes.
that the light hitting you, the stars died by the time you see
Yeah,
it.
it's millions of years old.
Wow.
If you think about it, one thing that I think is really cool to inspire like my little brothers, I just tell them everything that's happening here on Earth is recorded technically. If you could invent some sort of crazy teleportation device that could take you 27 light years away, so the distance light would travel in 27 years, but to take a super powerful telescope and look back at Earth, you would be looking at Earth in the 1990s,
Oh,
That's amazing.
cool.
which is really cool to think about. So
Yeah.
So we'd be able to see like all the Spice Girls in shell
Yes.
suits and all of those
Precisely.
horrible fashion
The really
decisions.
awful fashion. Yeah.
yeah.
Boyzone would still be there.
Yeah, I mean, you
Wow,
can
that's
see as
crazy.
far back into Earth's past as you want,
Wait,
as long as you can.
So if you went to a planet that was 10,000 light years away,
You
you'd
would
be able
see
to look back and see.
whatever Earth was like 10,000
So
years ago.
dinosaurs or whatever it might be that you're interested in, you could
Relatively
almost,
short.
presumably if you got to the point where you could build such a contraption, you could actually time and target whatever it was that you wanted to look
Yeah.
at.
So that's kind of time travel then.
Yeah, it
Oh.
really is.
So you just have to drive your spaceship to a distance away that is the time that you want to go to and look backwards.
And look back. Yeah.
Oh, that's so cool.
Could you go back and look at yourself?
You definitely
Yeah,
could.
well, you'd see yourself, wouldn't you?
Yeah. You
What would
wouldn't.
happen though if you saw yourself? I'm just imagining some...
So then if you went far enough away, would you be looking back at the Big Bang?
That is a really good question. That is a really, really good question. And you know
Let's
what?
do it.
You would be.
Yeah.
That's precisely how scientists study the Big Bang. Is they take whatever waves, and they might not be light waves, they might be radio waves, coming from as far back of the universe as possible.
Right, so they're going
Farthest
to the
away.
edge,
Yeah,
very far away,
very edge.
and looking back.
That's how you study how the universe is created.
Oh, that's mind-blowing.
And so on that note then, how the universe was created, that very much falls under the remit of the work at CERN, if I'm not mistaken, as well.
Yeah.
In a sense, trying to recreate
Yes.
those kind of conditions. Can you tell us a bit about that?
Yeah, so when you had the Big Bang, it was just a hot, dense ball of these particles, and not the complex particles that we have today that make up, me and you, like carbon, oxygen, helium, iron, silver, gold, all that. It was literally just particles. Something even smaller than these atoms that I'm talking about, like that you would see in the periodic table, are something called protons.
So it was a singularity? Is that a phrase that's still used?
Ooh,
Yeah,
singularity.
yeah, it can be put that way, yeah. And so you just have these subatomic particles, these protons, right? Such a high energy with each other, and they're smashing into each other. And then suddenly there was a big explosion, and then that was the beginning of the universe. And how CERN tries to study that is it accelerates these protons at super high energies, right? Almost at the
so
speed
it's
of
coming
light.
back to this underground tunnel where they're flying things around at
Yes.
super high speeds.
And
Like, what is going on under there?
also,
so-
They are
Yeah.
trying to recreate those conditions of the Big Bang,
yes,
those
yes.
early collisions.
Yes, and
Wow.
they smash these super high energy particle beams into one another and see what comes out.
I
They're
see.
trying to create like a mini Big Bang,
Okay.
basically.
We talked about particles, and you're saying it makes up everything that you can see and feel and hear and touch. And many people might be tempted to say, oh, so matter is everything in existence. But that's not quite right, is it? Because the universe and everything is not solely matter. There's other things as well.
Yes.
What percentage of the universe is matter?
5%.
That's insane.
Yeah.
So what on earth is everything else?
And off Earth.
And off Earth, what in the universe is everything else?
About 25% is something called dark matter, which is, you can think of it as the same thing as matter, except we just can't see it. And then the other 70%, which is the hugest chunk, is something called dark energy, which is a complete mystery to everybody.
So
Wow.
can you try and explain both of those things?
So, yeah.
Just in easy sentences.
Dark matter is a bit more well understood.
Uh-huh.
So how you see things usually is it reflects electromagnetic waves, which are light waves, right? And it reflects them, it hits your eye, and then you can see this object. And then depending on the wavelength, different colors. But dark matter doesn't have this interaction with the light waves.
Okay.
So light waves just go straight through them. So they're not detectable by light waves. And the same thing with radio waves and X-rays and gamma rays
Wow.
and microwaves. And
Right.
so they don't interact at all. So
It's almost like light shining on a mirror versus shining through a pane of glass or something. It just passes
Yeah.
straight through it.
yeah, straight
So
through.
this might be a silly question, but is it still made of particles? We don't
That's
know.
where we're trying to find out. Yeah. If it's made up of particles, it's a completely new kind of particle that we don't know anything about, that we've never come across before.
This is it. So if all of the technology that we have is only able to detect things within a certain range, then presumably we're almost at the limitations of what we're able to detect with our equipment. Much in the same way as, with human language, there are certain feelings or emotions that we might experience,
Yeah.
but we just can't
We
put a
don't
finger on
have
it because we
words
don't
for
have the
them.
language to describe
Yes.
it.
With colour. We had the visible light spectrum, and it was many, many years before we discovered infrared and ultraviolet light and X-rays and so on. So maybe there's just another wavelength that we haven't found yet in terms of the particle.
Yes, definitely. It could be that the particle interacts in some new way that we don't know about. So you can work out how much mass is in a system based on how fast it's rotating. And scientists were studying these faraway galaxies and studying their rotational speeds, and because you can see all the stars and all the planets, right? And based on all the visible light that they were getting, they could deduce what mass that galaxy had, and then you match it to the rotational speed and you go, hold on, that speed is about 55 times faster than it should be. It doesn't make sense. So there's got to be something else there that's adding to the mass, but we can't see it.
So we've got 5% is the matter that we can see and touch and interact with. 25% is this dark matter that we know must exist in order to make the math work. And the remaining 70% is
dark energy, which we don't know what it is. It's just empty space. It's, you know how they say the universe keeps expanding?
Yeah.
It's whatever fills that
but it's
expansion,
not nothing.
the void. We don't know what it is. We just call it
What do you
dark
think
energy.
it is? What do you think it is?
Yeah, I don't know. It's the universe keeps expanding, and it gets bigger and bigger, but what fills it?
But how do they know how much of the remainder is dark energy and how much is dark matter?
Yeah, that's a really
split.
good question. They do a rough calculation going back from the Big Bang and what size it was then, and then what size the universe is now, and just a rough estimate of how much matter we have in our world now. For example, this room would be 40% is your stuff. The other 60 is empty space.
Yeah.
Okay.
So do you see a time when we'll know what that is?
I don't think in my lifetime and our lifetime we're going to see that question answered.
But you're going to keep pushing the boundaries and getting us one step closer to figure out just what exactly is going on. And often when we look at research, especially publicly funded research, people feel as though they need to have some kind of tangible output, something that it's all leading towards. Whereas, Joanna, for your work, it seems it's very conceptual, it's theoretical. I mean, how do you think about that in terms of research for research's sake and not necessarily having that tangible output?
Yeah, that's a really good question. It's something I've always wondered a little bit, because if I had gone to psychiatry, for example, I would have been working with real patients, tangibly making some sort of a difference in somebody's life. But then you go into particle physics research and you're just really sitting there thinking, okay, what kind of real world impact is this going to have? It's to
for sure
get us one step closer into understanding, how is it that I am sitting here right now? How did that happen?
Well, actually, they're the big unanswered and potentially unanswerable questions, which, I mean, that's why religion exists, isn't it? Because we want to know where we came from and what's our purpose, who are we, all these sorts of big questions. So do you think that we need to frame our research in terms of its benefit to mankind, or do you think it's fine to just be poking around in the dark corners of the universe for the sake of it?
I think the second part of what you just said is completely fine, and I feel like that's the way it should be for research. Humans just need to know how they're here. They want their curiosity to be satiated, They have all these questions and they think, how did this happen?
I'm a movie nerd, and every character in a story has to have an origin story that makes sense, and quite often people fail to relate to a character in a movie if they don't know the background or where they came from. And it's the same with ourselves, we don't truly know ourselves unless we know our origins.
And then how do you know where you're going if you
don't know where you've been?
Understand your origins.
Right. Physics gets coupled hand in hand really well with philosophy, and some of the greatest physicists were also really, really great thinkers.
Let's imagine in 50 years, 100 years, 1,000 years, whenever it's going to be, we figure it out, and you figure out how the universe started and where we came from, and you answer it. What impact do you think that would have on society and religion and our culture?
Yeah, that's a big one. It's just like
we'll do another podcast dedicated.
I imagine if something so concrete like that, I mean, it's already the facts behind it is already pretty concrete right now, but I don't think maybe it's not as accessible if you're not in the scientific community, because you have all these big words that you don't understand. But Big Bang is very much, it's in the scientific community, it's accepted that's how the world came to be. But it might take a while for that to seep into the general public. But I imagine it'll have the same reaction that the theory of evolution did when Darwin first came out with it. I think there'll be a lot of struggle, and there is a lot of struggle.
The backlash, yeah.
But the theory of evolution doesn't actually disagree with, say, Christianity.
It's compatible with
They
it.
are compatible.
Yeah, even the Pope, I think, now is...
Even if you proved exactly the entire working mechanisms of the Big Bang from start to finish, it still doesn't mean there's not a creator or a ruler or something else.
Yeah.
So,
like who made the Big Bang happen?
Yeah.
I don't know.
Do you still think that justifies, for example, CERN being publicly funded? It's, taxpayers' money are going to answer these big questions. If somebody is religious and they're going, well, I know how I was created because my creator, they put me here. Why should we be paying for you guys to find out your version of the answer?
Yeah, I agree. If I have my way of thinking, why should my money be going towards something that isn't really too important to me?
Mm-hmm.
Well, the thing is, if you were to put one goal of CERN, it would be, okay, let's study how the universe came to be.
Uh-huh.
But then there are all of these side benefits that come out of it, and the entire technology industry is so rooted in physics, right? In CERN, one of the projects I work with was tiny little cameras, the little sensors inside the detector that allows you to see the particles, right?
Mm-hmm.
And these same sensors are in your smartphone, right? They're in your camera, they're in your laptop, they're in your TV, and the creation of these sensors was all motivated by research.
By this desire
Yeah.
to solve the big problems, we found all these smaller solutions as well.
Yes. So the World Wide Web, WWW, which I think it's safe to say that that's a pretty big thing now.
Never heard of it. What is this
Do we need
internet?
interwebs?
What is this internet?
Is it really necessary?
Yeah, no. So
that came out of CERN.
That came out of CERN, yeah.
As far as I understand, it was a way for scientists to share their data with each
Yes,
other. It's like
yeah.
a network,
Yes.
an internal
Yes.
intranet
Yes.
originally.
Yes.
And
Exactly.
then somebody said, hang on a minute,
We can make money.
we can make a lot of money from this.
Yeah.
there's a return on investment, guys. Thank you very much.
That's
Here's some cat
phenomenal.
video. Here's something.
It is phenomenal.
Yeah. So that's one huge thing that came out of this project that's supposedly research for research's sake.
I mean, that's a very convincing argument, isn't it, right there?
I'm sold. Yeah.
So actually, you could say in the same way that Star Trek inspired a lot of technology, like sliding doors and flip phones and so on, CERN is like the Star Trek for the world,
Yeah.
in that it's inspiring all of this technology.
Mm-hmm. So a lot of the funding actually comes from industry.
Uh-huh.
Well, that
So
makes sense. I guess,
Privatized
doesn't it?
companies,
Yeah.
and
Right.
they say, well, if you do that for your experiment,
We'll use it.
we'll mooch off the side
And,
benefits.
and what
there's-
about the military as well? Because I know that there's a huge amount of surveillance software and cameras and all that sort of thing we mentioned. Presumably, government funding, they can harness that and use that for things like military and surveillance
Definitely. Yeah.
as well.
But if I tell you the details, I'd have to kill you.
Oh,
Yes.
scary stuff.
So the Higgs boson is one of these tiny, tiny particles, and it's the particle that interacts with all other particles. So there are many particle types, but the Higgs is the one that interacts with all the other particles to give them mass.
It's the one that's friends with everybody.
Yeah.
Yeah.
What do you mean when you say to give them mass?
So the Higgs particle can't be thought of as a particle. It has to be thought of as a field. So you can think of it as a swimming pool, and if there was somebody who was like the Invisible Man,
Yeah.
or the Invisible Woman from Fantastic Four,
Okay.
if she were to be, walking out
She has a good
outside
origin
this
story, by the way.
this school, outside around the rim of the pool, nobody would see her. You wouldn't see her, and the water would be all still.
Yeah.
How you would see her though is if you push her into the water.
Okay, that
And
makes a lot of sense.
That's kind of what the
That's a good
I love
analogy,
that.
I like
Yeah?
That's good.
Does it work?
Yeah, that does work.
Yeah, so that's what the Higgs does. The Higgs field,
Like a medium of particles.
yes, all
Right.
together, all around us, everywhere,
Huh.
acts like this pool,
Interact with.
interacts with everything, all the other
Wow.
particles
It's
around
nice.
them.
So that's hugely important because then we can sort of, in inverted commas, see all the other particles
Yes.
Start to piece
through
together.
their interactions or
Yes.
the way that they move
Mhm.
Higgs boson
Mhm.
particles around.
Exactly.
Gosh.
So it's not all entirely intangible, I guess, when you start to
No.
think about it like that. This stuff, I think, is just truly inspirational and really does pique people's interest in science and technology more generally. And it's that real intangible, inspirational nature and this ability that it has to rally people up and get them interested, inspired, and passionate about these subjects. I mean, it's collaborative projects like that I think, really, really help to drive forward progress, technology, knowledge, and ultimately bring us to a better place than we were before.
Do you think that we need to have more publicity or more of a marketing campaign around what CERN is doing. I mean, obviously the Large Hadron Collider and so on is well known, the Big Bang and this idea, it was in the news a lot. But do you think we need an ongoing campaign to remind people or tell people what you're saying there, that very convincing argument for those naysayers who might sort of go, oh, it's a load of nonsense? My sort of example that I'm thinking of is with the space race. Obviously, massively influential, popularised patriotism and had this global following because it was marketed as this huge thing and everybody got involved. But arguably that was something that a lot of people would say is a pointless waste of money because it's just, like we said, exploration for the sake of it and so on. Now, obviously, following that same argument that you've already used, the technology that was developed at NASA ended up having lots of beneficial effects on all sorts of other things as well, in terms of materials science just being one field. But do you think we should be kind of having this huge big campaign of marketing what's happening at CERN now in the same way of we marketed the space race as being this final frontier and this huge thing that's got great public benefit?
I think that there needs to be a lot more advertising for the stuff that goes on at CERN. I think they do really great work, and they're the biggest physics research facility in the entire world. You know, it's CERN. It's not NASA. It's CERN. Not many people know about CERN.
Didn't know that until just now either.
Yeah, and it's because NASA does such a great job of selling themselves.
Oh yeah.
Yeah.
Right? They have a really good relationship with the public because they do a lot of outreach and they make their science easy to understand and accessible for the general public, right? People who don't come from a science background. For CERN, there's not too much of that. You just have your people doing your research, focused a lot on your research. And then, you know, if you're talking about the bridge between the scientific community and then your more general audience, I'd say that bridge is a little bit weak.
First of all, it's this tangibility thing. Rockets, right? You can see rockets. Second of all, I think
moon
that's
rocks
as kids boots. As well. It's like, wow, I would love to go on a rocket and go into outer space.
Yeah.
Thirdly, I
the
think
Big Bang. Come on, you know, we could
agreed.
frame that. We could make a.
You could jazz it up. You could sex it up. But I mean, the other thing they've got as well is Neil deGrasse Tyson. Anyway, this guy is an absolute rock star.
Yeah.
And again, when you've got
and they had Neil Armstrong and Buzz Aldrin. They had characters.
Right. And that's really captured the imagination of several generations and will continue to. Certainly, CERN would have its work cut out for it, but I think this information is sexy enough to lend itself to.
Elon Musk is a character, and Richard Branson with his sort of spaceflight Virgin Galactic, he's a character. You know, it's the Tony Stark billionaire lunatic inventor sort of story, isn't it? And maybe we don't have a figurehead for CERN. We don't have
Joanna Huang.
Yeah.
That would be me.
Thank you.
Are you going to be
the Elon Musk of CERN?
The poster child for CERN.
Yeah,
Why not?
That would be amazing.
And that would really tell those people who told you that a girl can't do physics.
On that note, then you've got to...
I've a couple of things I wanted to ask you. So firstly, you were actually at CERN when the collider started running in 2015?
Yes.
And this was a record-breaking event. Can you tell us, what was that like?
They had the particles running around the accelerator at higher energy than any other particle accelerator in the entire world. So the record before that was at, let's just call these arbitrary energy units, was at 7 TeV, which is this energy unit. And that was also set by CERN, and CERN broke its own record, and it was at 13, so twice the amount of energy. So it was really, really a big achievement.
Smashing that previous
And so
record.
what was the atmosphere like there? Did you get to were you part of that? You know, did you witness it? How does one see...
You don't necessarily
like a little
see
needle
it
on a computer.
You just you see it on a screen, right? And you see it on the screen, and you go, "Oh, there's the first collisions." And I remember being in my office with my fellow lab mates beside me, and then the moment the LHC started running again, the entire building from the first floor to the 5th, 6th floor. Everyone just got up and started clapping and cheering. And
electric.
Wow.
Yeah, and then somebody popped a bottle of champagne. It was a really big moment, and I think that was the moment when I just realized I want to stay in this field. That was a defining moment. Yeah, it was really insane. Yeah,
Amazing.
Amazing. So, and then you're working in something called Atlas, or with something called Atlas.
Yes.
Can you tell us a little
Yes.
bit about that, please?
So there's many experiments, so many detectors set up at different parts of the circular ring.
Mm-hmm.
And Atlas is one of the 2 general purpose detectors. It's huge. It's like 25 meters tall, 40 meters wide, so like a Olympic-sized swimming pool. And
So the one CMS?
the other one is CMS, yes indeed.
You're such a little nerd.
Yes.
Pretty please, yeah.
And
What does Atlas stand for?
the abbreviation is ridiculous. A toroidal LHC apparatus. It's yeah. I don't know. The abbreviations are a little bit.
But I mean, it's, when you put them together, Atlas sounds pretty badass
Atlas
to me.
is good.
I like
Atlas is good. Yeah, but
Great.
if you
I
gotta
think
break
that's
it down.
again. See, NASA is better at that, isn't it? This is where they.
Yeah, it's not that great.
Oh gosh. Okay,
Right,
so
cool. That's it.
what does Atlas do?
So Atlas has different types of sensors that they're like cylinders of sensors wrapped around each other, and what they do is they let you see the particles that go through it, and different parts of the detector are particle specific. They're meant for detecting different types of particles, right? Because you have some particles that are charged, like an electron or a proton.
Oh, okay.
Mm-hmm.
Some particles that are neutral, like a neutron, and there are many more like that.
Mm-hmm.
And then you have some particles that actually go through the detector altogether and don't get detected. So the Atlas is like a big camera that can give a snapshot of what happens when
Great.
these 2 proton beams collide. And what I do, which is on dark matter, working on Atlas, is the short version is that, okay, well, if this dark matter doesn't interact with anything, then our Atlas detector isn't going to see it. But we know exactly how much energy went into the collision. And based on what we can see, we can calculate how much energy there is
Okay.
of what we image, of what we can get. And then if there's a large chunk of missing energy, then we know, okay, maybe there was something there. Yeah. By now we know what to expect when these particles smash together. We know what comes out. So they have a very particular signature, and we know what to look for these signatures. But if you get something that is completely mismatched with your expected signature, then you got something new happening. And any of these could possibly be dark matter.
Amazing.
Awesome.
So cool. It's
All
like
right.
it's like chasing ghosts, isn't it? It's so cool.
Right.
Okay, thank you.
Usually we sort of wrap up with just a few quick questions, and so we've got just a few things to close off with before we say goodbye. If you weren't a scientist, what do you think you would be doing instead right now?
When you were
I think
younger.
I'd be an artist.
All right.
Yeah.
Yeah.
I think I'd be a painter.
A painter.
Yeah.
Like landscapes.
Painting whatever I look at that gives me emotion.
And what gives you emotion?
Oh, it depends. Sometimes it's a book, sometimes it's a cup, sometimes it's a leaf on the ground.
But all matter.
Ah, there you go.
It doesn't matter what it is as long
Does it matter? Oh, we nearly made it through the whole podcast without making
Without a pun.
About does it matter? Does
All right.
it matter? Okay. Is there an emerging field or technology that you're most excited to follow?
I think the sensor technology that goes into the Atlas detector. Yeah, so the little things that we use to actually image the particles, they're quite powerful. They're very small. They get down to the size of half a fingernail, and it's insane how these tiny things are what let us do all the research that goes on at CERN.
Yeah, it really is amazing, isn't it? Cool, thank you.
What is a topic in your field that is commonly misunderstood, that really frustrates you? If you could just wave a wand and have everybody understand this commonly misunderstood thing, what would it be?
How the Big Bang works.
Yeah,
It's quite
surely all of it.
Yeah.
Field.
I mean, I don't even understand it, and I've taken 3 courses that should give me the basis of understanding it.
Yeah.
But I really wish I could sit down with every single person and just give them what I know and more.
Yeah, well, that's what you've done over the last hour with us anyway.
Absolutely.
So,
So what is it that people misunderstand about the Big Bang? What's the kind of...
A lot of people know it's just a thing, you know, if one step above that, it's an explosion. But how did it actually happen? What are the processes? The Big Bang also had a lifetime of its own, you know, it's like first this, and then that, and then it was that. Yeah.
Maybe one day we'll get there, especially if everyone hears the podcast, then they will all know.
Oh, I hope they do.
You mentioned that incredible moment at CERN where you realised this is definitely the field you want to stay in. But before that, I'm thinking much younger. Was there ever a moment that you remember where you were first fascinated by science? The first time that you thought, this is for me, this is me.
Yeah, always. It was all those time travel movies. I was super into the geeky movies, the wormholes, the black holes that you would get. And I just remember watching those movies and thinking, oh my god, I want to be like one of those people on the spaceship.
And you've also spoken a little bit about some of the equipment that you work with. Do you have a favourite piece of equipment that you work with?
Oh, I gotta say, it's this machine that was in my lab back in Oxford. My supervisor will be happy I'm talking about it, but it's
Give him a shout out.
Yeah. Thanks, Daniela. It's this machine that it assembles the modules of these sensors that go into the Atlas detector, and the precision of it is absolutely insane. You just watch it work and you think, oh my god, I'm an iRobot. Yeah, so
Excellent.
So it's like a little robotic assembly.
It's a gigantic robotic assembly machine with exceptionally high precision.
And what's it called?
The pixel assembly module machine thing.
You've got to work on your
Amazing.
names,
Oh,
guys.
man.
Yeah, I know.
You've got to
We
get
need to
some
name
sexier
that.
names for your things. Okay, great. And yeah, just finally, can you tell us your favourite science joke?
Oh man.
Got a whole list of them.
You must have a lot. There's loads of physics ones.
Oh, okay. Oh god. Oh, you got me. I definitely do have a lot of physics jokes. I'm notorious for giving them. Okay, I'm gonna tell one that there's this something called Heisenberg's uncertainty principle.
Mm-hmm.
Heisenberg is the guy who came up with it, and the principle basically says that the better you know something's position, the less you know about its momentum. So if you know exactly where it is, you don't know how it's moving.
Mm-hmm.
If you know how it's moving, you don't know where it is. And that kind of makes sense, right?
Mm-hmm.
That's such a good way of explaining it.
Mm-hmm.
Yeah. So, one joke that I have is, why was Heisenberg bad in bed? Well, when he found the right position, he could never get into momentum. But when he was in momentum, he was never in the right position.
Boom.
Oh god.
Heisenberg, nice.
Yeah.
Brilliant.
Joanna, this has been a blast. Thank you so much for coming on
been a
and
pleasure.
sharing your work
Thank you.
with us. This has been great.
Amazing. So yeah, thank you so much.
Yeah.
My pleasure. You're listening to WonderLabs, colliding your boson holes with nerdy higlets. Wonderful!
Yes. Excellent.
That was really great. Thank you.